everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about Newton's rings. So if we look at the brief outline of Module 4, we have already discussed the Huygens principle, the superposition of waves, Young's double slit experiment, and we have also derived the expression for fringe width. Today we are going to discuss about Newton's rings. So when it comes to today's topic, how we are going to discuss this topic? First, we'll have a quick recap of the types of interference, and then we will understand the interference phenomena in thin films. This is very much required to understand Newton's rings. Then we will discuss the experimental setup for Newton's rings experiment. Then we'll derive the conditions for bright fringe and dark fringe, which is due to constructive interference and destructive interference. So after that, we are going to deduce the expression for the wavelength of the light that we are using. And also a very important application of Newton's rings experiment is to determine the refractive index of a given liquid. So this is what we are going to discuss today. So coming to the type of interference, the first one is division of wavefront. So when we are talking about interference, interference is due to the superposition of waves having the same amplitude and wavelength traveling in the same direction when they superimpose. Depending upon how they superimpose, we get constructive or destructive interference. But these imposing waves, how do we get them? So there are two types in that. First one is by the division of wavefront. So what is division of wavefront? A wavefront can be divided into two or more parts by the use of mirrors. So we take a single wavefront and we will divide it into two or more with the help of mirrors. So coherent sources can be obtained by dividing the wavefront, that is originating from a common source, by employing the mirrors or by prisms or lenses. So that is how we are going to get the coherent sources. Examples of division of wavefront are Fresnel biprism. Now coming to the division of amplitude. The amplitude of the incident wave can be divided into two or more parts. So we need at least two for superimposition. So how we are going to divide it is by partial reflection or refraction. So coherent beams can be produced by the division of amplitude. So with the help of partial reflection or refraction, we are going to divide it in terms of amplitude. And these beams, they travel different paths and they are finally brought together to produce interference. So when these paths or the beams travel different paths and they finally interfere with each other, we get the interference pattern. So the best example here is the Michelson interferometer and the Fabry-Perot interferometer. Now if we see in our day-to-day life, we see many cases where we see this interference phenomena. So whenever path lengths differ, the waves interfere, and if they travel through different media, if you are taking a ray of light which travels through two different media, maybe it goes from air to glass or from air to water, two different media, then what happens? The path lengths will differ. So when the path lengths differ, the two waves with different path lengths, when they interfere, then we get the interference pattern. So if there is a very thin film of material, a few wavelengths thick, it should be very thin, and the light will reflect from both the bottom and the top layer, causing interference. So this can be seen in soap bubbles and oil slicks. So when you see a soap bubble that is formed in the froth, so a ray of light that is reflected from the top layer And also from the bottom layer, if these two rays interfere, we get an interference pattern. And the same thing will happen with oil slicks also. Now we are going to see interference in a thin film by reflection. So what is happening in a thin film? So when light is incident on a plain parallel thin film, you take a thin film, and when light is incident on a thin film, I take a thin film like this. When light is incident on the thin film, some of it gets reflected from the upper surface. Some of it will get reflected, and the remaining is transmitted. So this is transmitted. And again, some portion of the transmitted light is reflected back. This light which is transmitted into the other medium or the glass slab will reflect back by the lower surface and emerges through the upper surface. Now it comes out from the upper surface. So these reflected beams will superimpose. So this is the beam which is reflected. This is the second beam which has undergone refraction and then is coming out. These two beams, when they interfere with each other, they superimpose and gives rise to an interference pattern. Now let us try to understand this interference in film with the help of this diagram. So what we see here is a thin film. We are considering a thin film. So this is the thin film. For us to understand, we have put it broad, but it is a very thin film. Now a ray of light is incident on it. Let AB be the incident light. And I is the angle of incidence. What is angle of incidence? The angle which the incident ray makes with the normal. This is the normal. A line drawn perpendicular to the surface. We call this as normal. So the angle which the incident ray makes with the normal, we call it as angle of incidence. Now at this point B, a part of light is reflected. This is the reflected ray. So we call it as light ray 1. So the ray that is incident and just reflected at the top surface. So we may call it as BG or the light ray 1. Now some part of it is refracted into the thin film. So this is the refracted light. And the angle which the refracted ray makes with the normal, we call it as angle of refraction R. Now this is the normal. This is the refracted ray. So the angle which the refracted ray makes with the normal, we are calling it as R. Now after it touches this surface, this transmitted ray will be reflected. And then it emerges out like this. So this we are calling it as light ray 2. Now what is happening here is the light ray 1 has simply reflected from the top surface, but the light ray 2 is going inside the thin film, undergoing refraction, and then is coming out. So from the geometry of the figure, we understand that the path traveled by the light ray 2 is more when compared to the path traveled by the light ray 1, because to understand interference, we have seen the conditions for constructive and destructive interference, that when these light rays are in phase with each other, then it gives rise to constructive interference, and when they are out of phase, it gives rise to destructive interference. But when will they be in phase? When the path length or the path traveled by the two rays is the same, or the path difference is an integral multiple of lambda, we get a constructive interference. So we need to understand what is the path that is traveled by the two rays, or we calculate the path difference between the two rays. Now we are considering a transparent plane parallel film of thickness T. So this is the thickness of the film. and the refractive index is mu. Mu is the refractive index. Suppose we are taking a glass slab, a thin film of glass. So the refractive index of it is considered as mu. Now let a monochromatic light ray AB be incident at an angle of incidence I. So we have seen this is the incident ray and this is the angle of incidence on the upper surface. Now BE and BC are the reflected and transmitted rays. So this is BE, which is the reflected ray, and this is BC, which is the transmitted. So BE is the reflected ray and BC is the transmitted ray. And let the angle of refraction be R. So this is angle R, the angle which the refracted ray makes with the normal is R, the angle of refraction. Now the ray BC will be reflected into the film and emerge through the film in the form of light ray DF. So this ray BC, after touching the surface, bottom surface, it gets reflected back and then emerges out as DF. So DF represents the light ray 2. Now these two light rays will superimpose. Which are the two light rays? The light ray 1, which is represented by BE, and the light ray 2, which is represented by DF. These two, when they arrive at a point simultaneously, they will superimpose. And depending upon the path difference between them, they produce interference pattern. So this is what we need to understand with the help of this diagram. Now to know the path difference. So whenever we want to understand interference, first thing we should know about is the path difference. So to know about the path difference, what we are going to do is draw a normal DG to BE. So we are going to draw a normal. Normal means a line drawn perpendicular. So this is a ray BG. So we are going to drop this normal DG. This is 90 degree. DG to B. On BE, we are dropping a perpendicular from the point D. So this is 90 degree. Now from the points D and G onwards, the light rays travel equal distance. If you see from the figure, from the symmetry of the figure, from this point and from this point, the light rays are traveling the same distance. So because we have drawn perpendicular from here and here, these two are parallel lines, and so the distance traveled by them is the same. So now what happens? From the points D and G onwards, the light rays travel equal distances. But by the time the light ray travels from B to G, the transmitted light has to travel from B to C and C to D. Means if you talk about the first ray, light ray, by the time it comes from here to here, now we are not talking about this. From G onwards, from D onwards, they travel the same distance. Now whatever the path difference that arises is due to BG and BC plus CD. So by the time the first ray travels from B to G, the second ray is traveling BC and CD and arriving at D. So that is the meaning. By the time the light ray travels from B to G, the light ray 1 travels from B to G. The transmitted light travels from B to C and C to D. So it is coming from B to C and then from C to D. Now the path difference between the two light rays 1 and 2 is given by mu into BC plus CD in the film minus BG in air. What we need to understand here is, when I am talking about BG, this ray is in air because it is reflected from the top surface from B. So when I am talking about BG, BG is in air. And when we see BC and CD, these two are inside the film of refractive index mu. So when we calculate the path difference, we also have to take into account the medium through which they are traveling. So for the second ray, it is mu into BC plus CD, that is the refractive index of the film, multiplied by the path traveled by the rays, minus BG in air. BG is the path traveled by the first ray, and that is in air. So how do we get the path difference? Is the difference between the two. So how do we now calculate from the figure BC, CD and BG? So in the next few minutes, we are going to see how do we calculate BC, CD and BG from the geometry of the figure. So for the first one, what we do, we consider triangle BCH. Which triangle is this? This is the triangle we are going to consider. BCH, this triangle. And this is R, the angle of refraction. So when we have to write cos R, so what is cos R? Cos is always adjacent side upon hypotenuse. Cos R is adjacent side upon hypotenuse. So which is the adjacent side for R? CH, and the hypotenuse is BC. And what is CH equal to? It is nothing but the thickness of the film. So BC. So if we have to calculate BC, we are going to take it on to the other side. So BC will be equal to T upon cos R. So what we get here, BC is equal to T upon cos R. So once we get BC, we can calculate CD also. If you see from the geometry of the figure, it is symmetric and the distance traveled is the same. So here, because it's reflection, we know the angle of incidence is always equal to the angle of reflection and the angles are the same. So the sides will be the same from similar triangles. So CD is equal to T upon cos R. So we want to calculate BC. So BC is equal to T upon cos R. We want to calculate CD. So CD is equal to T upon cos R. Now what is BC plus CD? So BC is equal to CD is equal to T upon cos R. Now the next thing what we have to calculate is BG. What is this? We have to calculate this value of BG. So to calculate BG, first we have to find BD. BD is an unknown thing for us. So first we will find BD. How do we get BD? BD is nothing but BH plus HD. So we are going to write BD is equal to BH plus HD. So how do we get BH and how do we get HD? So we are going to consider this triangle BHC again. This triangle, the same triangle we are going to consider BHC. And now we will write tan R. What is tan R? Opposite side upon adjacent side. Tan is always opposite side upon adjacent side. So which is the side opposite to R? It is BH. And the side adjacent is CH. And we know CH is equal to T. So we can simply write BH is equal to T tan R. Now this value BH is equal to T tan R. So again from the symmetry of the figure we get HD is also equal to T tan R. We want BD. We want BD. BD is BH plus HD. So BD will be equal to T tan R plus T tan R. That will be 2T tan R. So this is a very important relation. So we have first calculated BD. And from this we are going to calculate BG. So from the figure BDG, now we are going to take this right angle triangle. This is the right angle. Sin I, this angle is I. So sin A will be opposite side upon hypotenuse. So it will be BG upon BD. So BG will be equal to BD sin I. We are writing from this. From the figure, because this is I, we have sin I is again opposite side upon hypotenuse. So BG upon BD. And BG will be equal to BD into sin I. And just now we have calculated BD. So what is BD equal to? 2t tan R into sin I. Now we are going to substitute for sin I also. We know from Snell's law mu is equal to sin I upon sin R. This is our famous Snell's law. The refractive index is given by the ratio of the sine of the angle of incidence to the sine of the angle of refraction. So we can substitute now for sin I is equal to mu sin R. So in this expression for BG, let us substitute mu sin R. So what do we get for BG? BG will be equal to 2t tan R into mu sin R. Or we can rearrange the terms and write it as 2 mu t tan R into sin R. Now we are going to substitute these values in equation 1. What was our equation 1? To get the path difference. The path difference is given by mu BC plus CD minus BG in air. So we have already calculated BC and CD. BC is T by cos R and CD is also T by cos R. So we get mu into 2T by cos R. And now we got BG as 2 mu T tan R sin R. This is what we got. We have substituted here in equation 1. What we are going to get is the path difference. 2 mu T by cos R minus 2 mu T tan R sin R. Now we are going to simplify this because we know tan R is equal to sin R upon cos R into sin R we have. So sin R into sin R is sin square R upon cos R. So we have 2 mu T. Instead of tan R, we have substituted sin R by cos R multiplied with sin R. We are getting sin square R upon cos R. So in both the things, whatever is common, we are going to take it out. So 2 mu T in the numerator is common and cos R in the denominator is common. So we are going to take out 2 mu T upon cos R as common. So we are left with 1 in the first term. And in the second term, we will have sin square R. So because 2 mu T by cos R, we have taken outside common. So we are left with only one term, sin square R. So 1 minus sin square R. And we all know sin square plus cos square is equal to 1. So sin square R plus cos square R is equal to 1. So 1 minus sin square R will be equal to cos square R. So for 1 minus sin square R, we are going to substitute cos square R. And then this cos R and 1 cos R will get cancelled and we are left with 2 mu T cos R. So what is the path difference now between the two rays? 2 mu T cos R. The path difference between the rays, light ray 1 and light ray 2, we have arrived at this expression 2 mu T cos R. Now at the point B, the reflection occurs from the upper surface of the thin film, that is the denser medium. So the light ray undergoes an additional phase change of pi or an additional path difference of lambda by 2. So whenever there is a path difference of lambda, there will be a phase difference of 2 pi. So for a path difference of lambda by 2, it will be pi. So what we are seeing here is because it is from one medium to the other, there is always a phase change of pi, and which corresponds to a path difference of lambda by 2. So now what will be the total path difference? 2 mu T cos R we have calculated, and now an additional path difference of lambda by 2. So the total path difference will be 2 mu t cos r plus lambda by 2. Now the path difference is equal to integral multiple of lambda. Then the rays 1 and 2 will meet in phase. So we have already seen these conditions when we understood interference patterns. So where we have already calculated the path difference. If the path difference is an integral multiple of lambda, they will meet in phase and we have constructive interference, and constructive interference gives rise to bright fringe. So we are going to put the condition. So what is the path difference? 2 mu t cos r plus lambda by 2 is equal to n lambda. So this is the condition. If the path difference is an integral multiple of lambda, we will have constructive interference. So we are going to substitute it here. So 2 mu t cos r will be, if I take this lambda by 2 on the other side, what does this imply? 2 mu t cos r will be equal to n lambda minus lambda by 2. So the same thing we can write it as, if I'm taking LCM as 2n lambda minus lambda, or 2n minus 1 into lambda by 2. Both are the same. This and this is the same. So we are writing it as 2n minus 1 into lambda by 2. So if the path difference is this, we get a bright fringe. This gives rise to bright fringe because of constructive interference. Now, when the path difference is equal to half integral multiple of lambda, half integral multiple or odd multiple of lambda by 2, then they will meet out of phase and we get destructive interference, and destructive interference gives rise to dark fringe. So what is the condition now? 2 mu t cos r plus lambda by 2, this is the path difference. And if this path difference is an odd multiple of half the wavelength, so suppose we put n is equal to 0, we get lambda by 2. N is equal to 1, we get 3 lambda by 2. So for lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on. So half odd multiples of lambda by 2, of lambda. So 2n plus 1 into lambda by 2. So we are taking these and simplifying. So what do we get? 2 mu t cos r will be equal to 2n plus 1 into lambda by 2 minus lambda by 2. We have brought this lambda by 2 onto the right side. So expand it, what we have? N lambda plus lambda by 2 minus lambda by 2. Minus lambda by 2 plus lambda by 2 will get cancelled. So we get 2 mu t cos r is equal to n lambda. So we are going to write the condition for dark fringe. So where n takes the values of 0, 1, 2, 3 and so on. So depending on these two conditions, if 2 mu t cos r is equal to 2n plus 1 into lambda by 2, we get a bright fringe. When 2 mu t cos r is equal to n lambda, we get a dark fringe. So depending on the above conditions, the interference pattern consists of bright and dark fringes. So now with this background of a thin film, we have already derived the conditions for a thin film. What is the condition for constructive interference, which gives rise to a bright fringe? What is the condition for destructive interference, which gives rise to a dark fringe? So with this in mind, we are now going to understand Newton's rings, how Newton's rings are formed. Newton's rings, they are one of the best examples for interference in a non-uniform thin film. So here it is a thin film, but the film is non-uniform. So whenever we are talking about Newton's rings, we need to understand what we are going to observe is the interference pattern in a non-uniform thin film. Now what do we have here is a plano-convex lens with its convex surface is placed on a plain glass plate. So if you see in the figure here, this is the plain glass plate. This is the plain glass plate. And this is a plano-convex lens. Plano-convex means one side of it is plane and the other side is convex. So we have taken a plano convex lens and we are putting it on a glass plate, on a thin glass plate. So then what happens? An air film of increasing thickness is formed between the two. So between the glass plate and the plano convex lens, you see here this region is nothing but air. So when we are keeping the system open, so there is air in between. Now, if you see the thickness is varying at the point of contact, the thickness of the air film is 0. And as you go from the center away, the thickness of the film goes on increasing. On either side, it is symmetric. So at the center, the thickness is 0. But as we move on to the right, the thickness is increasing. And the same thing as we move on to the left, the thickness is increasing. So what we understand here is ray 1 undergoes a phase change of 180 degree on reflection. Now here, if you see a ray of light that is incident here, this is one reflected ray and the other transmitted ray which is going inside the air film, getting reflected back and emerging out. This is one. So this one is undergoing a phase change of 180 degree. And ray 2 undergoes no phase change. This one does not undergo any phase change. And also here, capital R represents the radius of curvature of the lens. What is radius of curvature of the lens? When we are talking about a convex lens, suppose I am taking out this part. This forms a plano convex lens. Now, this lens is a part of a spherical surface. So the radius of this spherical surface of which the lens forms the part, we will call it as R, the radius of curvature. And small r represents the radius of the Newton's rings. So we'll be seeing the rings that are formed here like this. So small r represents the radius of the ring that is formed. Now how do we see the rings? If monochromatic light is allowed to fall normally and the film is viewed in the reflected light. So we have seen the setup. We have a plain glass plate on which we are placing a plano convex lens. So between the plano convex lens and the glass plate, there is an air film that is formed. And the thickness of the air film is not uniform. At the center, at the point of contact, the thickness of the film is 0. And as we move away from the center, the thickness increases. Now, if we allow light to fall onto the film, onto the air film, and you view it in a reflected light, then what we see is alternate dark and bright rings concentric around the point of contact between the lens and the glass plate are seen. So we imagine this is the point of contact between the lens and the glass plate. So from here you will see concentric rings like this. These are concentric circles. So what we are seeing here is a dark, bright and so on, concentric. These rings are circular and are observed by Newton. So we are calling them as Newton's rings. So these rings are named after the scientist Newton who discovered this pattern. Okay, so we are now going to understand how these rings are formed and the experimental setup for it. So what is the experimental arrangement to view these Newton's rings? So this part we have already discussed. We have a plain glass plate. This is the plain glass plate. And on this plain glass plate, we are placing a plano convex lens. One side is plane and the other side is convex. So we are placing a plano convex lens. Now what we have seen, when light is incident here normally and you view it in the reflected light, you will see the Newton's rings. So to get the light to fall onto it normally, we have a source. The source we take here is a sodium lamp. Sodium lamp is a monochromatic source. This is a monochromatic source. Monochromatic means light of single wavelength. So we are taking light of single wavelength and this light is allowed to fall on this setup normally. So for that, what we do is we keep a glass plate G inclined at an angle of 45 degree to the horizontal. This glass plate, which we also call it as beam splitter, we may also call it as beam splitter. How we are placing this glass plate? At an angle 45 degrees to the horizontal. So the rays that are coming and falling on this glass plate, which is kept inclined at an angle of 45 degree, will be now reflected onto the air film. So the light is now incident on the air film. This is the air film here. The thickness of the air film is 0, and as we go away, it is increasing. So now how light is incident? It is incident normally, and the reflected light is viewed with the help of a traveling microscope, because these rings are very small, and if you have to calculate the distance between the rings or anything, you may not be able to do it with a naked eye, even though you are able to see the rings. So we need a traveling microscope to view the rings. So we are viewing them in reflected light. So this is the experimental setup. Now what we have seen, a plano-convex lens of large radius of curvature is placed with its convex surface on the plane glass plate. So this is the convex surface, this is the glass plate. So the convex surface has to touch the plane glass plate. Now the lens makes the contact with the plate at O. So this is the point of contact, which we call it as O. Now monochromatic light falls on the glass plate G, held at an angle of 45 degree with the vertical. So this is the glass plate G, which is held at an angle of 45. If this is 45, with the vertical also it is 45. Now the glass plate G reflects normally a part of the incident light through the air film enclosed by the lens and the glass plate. So the air film is enclosed between the glass plate and the convex lens. So this light is now falling normally on this film. A part of the light is reflected by the curved surface of the lens, and a part is transmitted, which is reflected back from the plane surface. Means when light ray falls here, suppose a light ray falls here, normally it is reflected here, some part of it is transmitted and then reflected. So we are going to see both. Sorry, you can see it like this from here. Now this is a better picture to understand. So what we are talking about is a ray that is incident normally. A part of it is just reflected from the bottom surface of the convex lens, and a part of it is transmitted through the air film. This is how it is transmitted through the air film, and then it is coming out. So this we call it as ray 1 and this is ray 2. Now if these two rays interfere with each other, we get the interference pattern. Now Newton's rings are formed due to interference between the light rays reflected from the top and the bottom surfaces of the air film. So this is the light ray that is reflected from the top of the air film, and this is the ray that is reflected from the bottom of the air film. Now a part of the monochromatic light AB is reflected at B. So this is reflected at B. What is B? This is the glass air boundary in the form of ray 2, and without an additional phase or path change. If the path does not change, there is no change or no additional phase. Then the other part is refracted along BC. So this is the refracted part from B to C. Why we are calling it as refraction? From glass, it is coming into air. So that definitely there will be a bending of the light, which we call it as refraction. So it is refracted along BC. And then at C, so this is the point C, which is the boundary for air and glass. It is reflected back, and with an additional phase change of pi or a path difference of lambda by 2. So now if you see these two rays, which will interfere, there is a path difference of lambda by 2 or a phase difference of pi. Now, because we are seeing the rays in the reflected light, and we have calculated the path difference between them as 2 mu t cos r plus lambda by 2. In any thin film, we have derived this condition for path difference 2 mu t cos r plus lambda by 2. Now, for this particular case of Newton's rings, we are going to put the conditions. Let us take 2 mu t cos r plus lambda by 2. This is the path difference for an air film, thin films. Now, the first condition we are going to put is mu is equal to 1. Mu is equal to 1 for air. We are talking about the air film, so the refractive index is 1. And at the point of contact, we have t is equal to 0. And since it is falling normally, normal incidence r is equal to 0. So, let us put these conditions here. So, what we get is 2 mu cos, mu is 1. So, 2 into 1 into t into cos 0 is again 1 plus lambda by 2. So, you get 2t plus lambda by 2. And then again t is equal to 0. So, you are getting lambda by 2. So, what is the path difference now? Lambda by 2. So, we are going to put all the three conditions in this equation. T is 0, mu is 1 for air and r is 0 for normal incidence. So, what we get, the path difference equal to lambda by 2. So, that is what we are writing here, path difference is lambda by 2. So, in the reflected light at the point of contact, the ray suffers a phase change of pi. So, I told you whenever there is a path difference of lambda, there is a phase change of 2 pi. So, here we have a path difference of lambda by 2. So, the phase difference will be pi. So, there is a phase change of pi. Now, the incident and the reflected lights are out of phase and they interfere destructively. So, the incident light and the reflected light are out of phase because the path difference is an odd multiple of half the wavelength. So, it gives rise to destructive interference. Destructive interference means dark spot. So, the central spot is always dark. So, you need to understand this is a reasoning question. Why is the central spot dark in Newton's rings? Because we are viewing it in reflected light. These are the three conditions we are going to substitute and we are going to see that the path difference is lambda by 2. So, whenever there is a difference, path difference of lambda by 2, they are always out of phase and out of phase gives rise to destructive interference which we will be seeing as a dark fringe. So, the central spot is dark. Now, the condition for the bright fringe. So, what is the condition for bright fringe? We have seen 2t plus lambda by 2 is equal to n lambda. This should be an integral multiple of lambda, or we can rearrange the terms and write 2t is equal to n lambda minus lambda by 2, or we can take out 2 LCM and take out lambda also outside. We get 2n minus 1 into lambda by 2. So, 2t is equal to 2n minus 1 into lambda by 2, where n takes on the values 1, 2, 3 and so on. Now, the condition for the dark ring. 2t plus lambda by 2 should be equal to 2n plus 1 into lambda by 2. If n is equal to 0, we get lambda by 2. N is equal to 1, 3 lambda by 2 and so on. So, this is the path difference we have got and this is the condition for the dark fringe. So, when we compare, so 2t plus lambda by 2 is equal to 2n plus 1 into lambda by 2. So, let me rearrange the terms and write. So, 2t plus lambda by 2 will be equal to 2n into lambda by 2 plus lambda by 2. 2 and 2 will get cancelled. So, this is n lambda plus lambda by 2, 2t plus lambda by 2. So, lambda by 2 and lambda by 2 will get cancelled and 2t is equal to n lambda. So this is the condition. 2t is equal to n lambda, where n takes on the value 0, 1, 2, 3 and so on. So for monochromatic light, the bright and dark fringes or rings depend upon the thickness of the air film. And for a Newton's ring system, the focus of the points have the same thickness, lie on a circle having the center as the point of contact. So we get bright and dark circular rings with the point of contact as the center. What does this mean? If you have the center, we have seen that the central spot is always dark. This is the point of contact. So after that you have a bright ring, then again a dark ring, bright ring, dark ring. So they are concentric rings. Now symmetric to the point of contact. So we get bright and dark circular rings with the point of contact as the center. Now how do we calculate the diameters of these rings? So we have discussed that we are getting the rings like this with the central spot dark and bright followed by dark and so on. Now suppose I want to find the diameter of the rings. So this is the first ring, dark ring. So this gives us the diameter of the dark ring, first dark ring. So you can calculate the diameter of the dark rings as well as the bright ring. So here I am talking about the dark ring. So what is it we are going to understand? We have seen that L be the lens that is placed on the glass plate P. So P is the glass plate on which we are placing the lens. Actually, till now we have been talking only about a plano-convex lens. This is the plano-convex lens. But to understand its radius of curvature, I told you, this is a spherical surface of which this lens forms the part. So here we are showing the full view of the lens. Means here this will be the distance from the center to the circumference gives us the radius of curvature. So this is the radius of curvature either from here to here. So we are denoting it by R. R represents what? The radius of curvature. So the convex surface of the lens is a part of the spherical surface with the center C. C is what? Center of the spherical surface of which this lens forms the part. And capital R be the radius of curvature and small r be the radius of the Newton ring. So here you see this is the radius of the Newton ring. So if you see here what is it? So if this is the diameter, so from here to here this is the radius. That is what you need to understand, relate to these two diagrams. If this total is the diameter, this distance gives us the radius. So this here NA or NB represents the radius of the Newton rings. Now the thickness of the film is denoted by T. What is it? From the property of triangles we see, or sorry, property of circles. It's not a triangle. We are talking about a circle. From the property of the circle, we have NA into NB will be equal to NO into NB. This is the property of circles. NA into NB is equal to NO into ND. These are the chords. So substituting the values. What is NA equal to R? NB is also equal to R. That is the radius of the Newton ring. And NO is nothing but the thickness of the film. And ND here. How do we get ND? OD is nothing but the diameter of the spherical surface. That is nothing but 2R. And ON is T. So we can write it as 2R minus T. So the total distance is 2R. That is the diameter. And this distance is T. So if I want the distance from here to here, it is 2R minus T. So what we have here, R square is equal to T into 2R minus T. Now as T is very small, T square is negligible. So we can write R square is equal to 2RT. So in this what we have, R square is equal to T into 2R minus T. So let us expand it. R square is equal to 2R into T minus T square. So this is negligible because T itself is very small. The thickness of the film is very small, we have seen. So this is negligible. We are neglecting the term T square. So what we are left with, R square is equal to 2RT. So T will be equal to R square. This implies if you are taking 2R onto the other side, T will be equal to R square upon 2R. Now for bright fringe, what is the condition? We have already derived this 2T is equal to 2n minus 1 into lambda by 2. And now we have got T also. So we are going to substitute now. 2 into, in place of T, we are going to put R square upon 2R. So T, in place of T, we are putting R square upon 2R. And the right hand side remains the same, 2n minus 1 into lambda by 2. This 2 and 2 will get cancelled. So we want to write R square. So R square will be equal to, we can take capital R onto the other side. So 2n minus 1 into lambda R by 2. So this is what we are getting. Now we are going to replace R by D by 2 because the diameter is nothing but twice the radius. So R will be equal to D by 2. So we are going to replace R with D by 2. So in place of R square, we will write D square by 4, squaring on both the sides. So D square by 4 is equal to 2n minus 1 into lambda R by 2. Now D will be equal to what if we are taking 4 onto the other side and taking the square root. So it will be 2n minus 1 into 2 lambda R. So 2 and 2 will get cancelled. Here I'll write D square formula. D square is equal to 4 into 2n minus 1 into lambda R by 2. This 2 will go 2 times. So we have D square is equal to 2 into 2n minus 1 into lambda R. If you want D, take the square root on both sides. So I'll just rearrange them and write into 2 lambda. So I've just put this 2 here. So 2n minus 1 into 2 lambda R. So we are getting 2n minus 1 into 2 lambda R. Now lambda and R are fixed for a given setup. The wavelength of light will not change and the lens, the radius of curvature of the lens is not going to change. So what is going to vary is n. N is the order of the ring. So now D is proportional to under root 2n minus 1. So what does 2n minus 1 give us? It gives us an odd natural number. So the diameter of the ring, bright ring, is always proportional to the square root of odd natural number. So the diameter of the bright rings are always proportional to the square root of odd natural numbers. Now for dark ring. For dark ring, what is the condition? 2t is equal to n lambda. And we know t is equal to r square upon 2r. So we'll substitute this condition. So put t is equal to r square upon 2r. So 2 and 2 will get cancelled. We have r square is equal to n lambda r. So now again for in place of r, we are going to substitute d by 2 whole square is equal to n lambda r. So d square will be equal to what? 2 square will be 4. Taking it on to the other side, 4n lambda r. So d square is equal to 4n lambda r. Or if we want d, taking the square root on both sides, 2 will come out under root n lambda r. Lambda and n are constants for a given setup, the wavelength and the radius of curvature. So d is proportional to square root of n. That is the natural number. So what we are trying to understand here is the diameters of the dark rings are proportional to the square root of natural numbers. And with the increase in the order, the rings get closer and the fringe width decreases. So when you see the fringe width, means the distance between any two dark fringes or any two bright fringes, it keeps on decreasing. Now, how do we determine the wavelength of the light source? Using this Newton's rings experiment. Now we know capital R is the radius of curvature of the plano-convex lens and wavelength lambda is the wavelength of light used. Now we are calculating the diameters of the mth ring and the nth ring. So we have seen this is the dark spot. This is one ring. We are talking only about bright rings. So this is the diameter of the nth ring, and this will be the diameter of the mth ring. So this is dm and this is dn. So dm and dn be the diameters of the mth and the nth ring. So this is the mth ring and this is the nth ring. Your n can be 1, m can be 2. So the diameter of the second ring minus the diameter of the first ring. So we have d square is equal to 4n lambda r, we have seen now. So for the mth ring, it will be dm square is equal to 4m lambda r. M represents the number of the ring. So the diameter of the mth ring, that is dm square, will be equal to 4m lambda r. Now the diameter square of the nth ring will be dn square is equal to 4n lambda r. We are talking about mth ring and the nth ring and trying to write their diameter squares. So once you get these two equations, dm square minus dn square will be, if we are subtracting on the left hand side, we do it on the right hand side too. So we have 4m lambda r minus 4n lambda r. So whatever is common, we are going to take 4 is common and lambda r is also common. So we are putting it like this. 4 into m minus n into lambda r. So we want to find lambda, that is the wavelength of the light source. Whatever light source we are using, what is the wavelength of it? So that is denoted by lambda. So if we want lambda, we will take 4 m minus n into r onto the other side. So lambda is equal to dm square minus dn square upon 4 into m minus n into r. Now, by calculating the diameter of the rings of the mth ring and the nth ring, and if you know the radius of curvature of the given plano-convex lens, you can very well calculate the wavelength. And the other way also is possible. Sometimes you are given the wavelength of the light and you are asked to find the radius of curvature. So if you have to find the radius of curvature, you can as well write it as r is equal to dm square minus dn square upon 4 into m minus n into lambda. So this gives the radius of curvature. So even during the experiment, if the value of the radius of curvature is given, by finding the diameters of the rings, you can calculate the wavelength. Or if the wavelength is given, you can calculate the radius of curvature using this formula. Now, how do we calculate the refractive index of a given liquid? So, if you want to find the refractive index of any liquid, how do we calculate it using this Newton's rings experiment? Again, we consider r be the radius of curvature of the plano-convex lens and lambda be the wavelength of light used. So, now we are using the same setup. We have a plain glass plate. On the plain glass plate, we are keeping a plano-convex lens. Then there is an air film that is formed between the two. And because of the air film, when we see the reflected light with the help of a microscope, we are seeing the rings, Newton's rings that are formed. And we are trying to calculate the diameter of the rings of the mth ring and the nth ring. Let dm and dn be the diameters of the mth and the nth rings. So we can write from the formula dm square is 4m lambda r and dn square is equal to 4n lambda r. And if you are subtracting dm square minus dn square is equal to 4 into m minus n into lambda r. Let this be equation 1. This is the setup we have put only in air. Okay. So first we are doing the experiment in air and we are trying to calculate the diameters and find dm square minus dn square. Now the system is placed into a container. The entire system is placed in a container which consists of the liquid whose refractive index is mu. So the liquid whose refractive index we have to find is taken in a trough or in a container. And the setup of the plain glass plate with the convex lens is kept inside that liquid whose refractive index we have to find. Let the refractive index of the liquid be mu. Now With this setup, we are going to find the diameter of the rings. Now, dm prime and dn prime be the diameters of the mth and nth rings. Now, the diameters will definitely vary. So, dm prime and dn prime are the diameters of the mth and nth ring when you kept it immersed in the liquid. So, once we are doing without the liquid, we have got dm square minus dn square. Now, we are keeping the system immersed in liquid and we are trying to find the diameters. We get dm prime square and dn prime square. So, dm prime square and minus dm prime square will give us 4 into m minus n lambda r by mu. So, if you see here 4m lambda r by mu, 4n lambda r by mu. So, when we are doing dm prime square minus dn prime square, it will be 4m lambda r by mu minus 4n lambda r by mu. If you rearrange the terms, we get 4 into m minus n into lambda r by mu. Now, our aim is to find the refractive index of the liquid. So, I will take mu onto the other side and write the formula. If I take mu onto the other side, we have 4 into m minus n into lambda r. And in the denominator, we have dm prime square minus dn prime square. Now, from equation 1, what equation 1 tells us? From equation 1, dm square minus dn square is equal to 4 into m minus n into lambda r from 1. So, we are going to substitute for 4 into m minus n into lambda r dm square minus dn square. So, mu will be equal to dm square minus dn square upon dm prime square minus dn prime square. So, we can easily calculate the refractive index of a given liquid knowing the diameters of the rings that are formed. First, dm and dn represent in air, dm prime and dn prime represent in the given liquid. So, we can very well calculate the refractive index of the liquid. So, thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.